Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 11, Section 4, titled Angle Measures and Segment Lengths. By the end of this video, you will have reviewed recent lessons describing angle measures and segment lengths. Discussions will include finding angle measures and finding segment lengths. In addition to reviewing angle measures and segment lengths, we will review a couple real-world problems involving the same. If you would like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find the video to be helpful. Thank you. Okay, definitions 11-4. We have one definition here. A secant. A secant is a line that intersects a circle at 2 points. That's it. It's a line intersects a circle at 2 points. It's called a secant. Objective 1A, finding angle measures. A secant line is a line that intersects a circle at 2 points. AB, the ray AB, is a secant ray. And you see it right here on the right-hand side. It has the arrows on each side, so it's a secant ray, right? This AB, secant ray. And AB is a secant segment. So it's just talking about the two dots defining AB as a segment. So angles formed by secants, tangents, and chords intercepted arcs on circles. And they intercept arcs on circles. The measure of the intercepted arcs can help you find the measure of the angle. So we have, looking down here at Theorem 11:11, it says the measure of an angle formed by two lines that, in case 1, intersect inside the circle is half the sum of the measure of the intercepted arcs. So in this case, you have this angle 1 right here is formed by the intersection of these two rays, and the intersection of these two rays cause two intercepted arcs. We have the arc from X and the arc from Y. Well, what they're saying is that the measure of 1 is equal to half the sum of the two arcs. So you add X and Y together and take half of it, and that's the sum of angle. That is angle 1. And we know how to measure half the angle and half the angles. You're familiar with that with the intercepted, right? We talked about that a couple slides back. So the included angle stuff with the tangent and the chord. Okay. Or 2 intersect outside a circle is half the difference of the measure of the intercepted arcs. So in this case, 1 right over here, let's look at this one right here. Angle 1 is formed by the intersection of two rays or lines of whatever type, rays in this case, outside the circle. And when they intercept outside the circle and they cut across the circle in two spots, as you see here, then angle 1 is half the X, the outer one, minus the inner one. Half of X minus Y. So if X is 100 and Y is 50, well then this angle is half of 50, which is would be 25. So it's very interesting. Okay, moving on. Okay, objective 1B, finding angle measures. So given circle 0 with intersecting chords AC and BD, they're easy to see here on the right. Prove that angle 1, here's angle 1, right? Easy to see. Angle 1 is equal to half of BA and C plus CD. So, how do we solve that? Well, what they've done here is they've begun by drawing AD. They put this line right here, this dashed line, AD, through here. And this is actually pretty ingenious, because once you do that, you know that this triangle. What do we know about? It's easier to start here, I think. If we start at this triangle that we just formed, we know that due to the exterior angle theorem, right here, exterior angle theorem, that this angle plus this angle, right, okay, let's put it this way, plus this angle, oh, this right here, that angle equals 180 degrees. Well, these two angles, if this is equal to the supplement of these two angles, this angle 1 has to be equal to angle A and angle D, because this here part here in the middle is what's left. I'm going to draw red. Let me get some red. This piece here is what's left after you add these two together. So that's the supplement. So now you see the angle, the line goes through and the angle is created here. So this piece on this side has to be equal to these two angles. So now we know that angle 1 is equal to angle A and angle D. So what are angle A and what are angle D equal to? Well, angle A, CDA, is equal to half of CD. And angle BDA is equal to BDA, that angle is equal to half of AB. So now let's look on this side. Now given that, let's look over here. It says angle BDA right here, is equal to half of BA. And we know that it's from this one here, the angle D, that this angle D is half of BA. So BDA is equal to half of BA right here and half of CAD. CAD, because these two together have to equal that angle 1. That's pretty ingenious. So now we come down here, we start substituting and putting it together. It says that angle 1 is equal to half of MA of BA, half of BA, and half of CD. And given that, we have angle 1 is equal to 1/2 measure of angle AB plus CD. So I've said it a couple times now, but that's exactly what it is. And it all has to do with this external angle theorem, which is based on this straight line and an angle. So you have everything on this side of the line and everything on this side. Well, everything on this side is everything that these two, A and D, are not. So when you add this side, the angle 1 has to be equal to angle A and angle D. The sum of angle A and angle D. Very ingenious solution. I like it. Okay, example 1, finding angle measures. Find the value of each variable. So in problem A, the variable is angle X, or this right here. Angle X is how many degrees is what they want to know. Where's my pencil? There, I'm sorry. There's my pencil right there. They want to know this angle. Well, according to theorem 1111, if the angle intersect inside the circle, then it's the sum. This angle here is the sum of these two angles. So, or it's one sum of half of those, okay? So we have X is equal to 1/2 46 plus 90. X equals 68. Okay? If we go to B, it's different because now the lines intersect outside, okay, the circle. Well, then in that case, it's the outer part, the outer arc, minus the inner arc. So 95 minus Z is equal to 120, is equal to 20 degrees. So 20 is 1/2 of 95 minus Z. And if we work it out, then 40 is equal to 95 minus Z. Z is equal to 55. Okay? So if the cross is inside of the two, if the two chords, if they're crossing here, the two lines, the rays, whatever they are, if they're intersecting inside the circle, you add these two right here. You add, those can be added together. If you know them, you can add them and you can take half of that value and come up with the angle right there, the angle. And if it's if they intersect outside, then you subtract, literally you're subtracting the outer one from the inner one. Or let's say the inner one from the outer one. I got to get that minus straight. It's the outer minus the inner, okay? Okay, Example 1, check your understanding. Find the values of each variable, and the variables they want in A is W and in B is Y. So you go ahead and stop the video and try these out, and when you come back, we'll take a look at it. Okay? Okay, so I'm assuming you stopped it, you've worked them, and you're back. So let's move on and give these a shot. So for problem A, what do we have? We're going to write an equation. And the equation that I'm going to write says, I'll do it right down here. 70 is equal to 1/2 W minus 110, because these lines intersect outside the circle, so you don't add these two arcs, inscribed arcs. You subtract the larger one or the smaller one from the larger one. So we have the W minus, or the outer one minus the inner one. We have W minus 110. So now we're going to clear the half from both sides. So we're going to have 140 is going to be equal to W minus 110. We're going to add 110 to both sides. So we're going to get 250 is equal to W. So for problem A, W is 250 degrees. Let's do B. B is basically the same thing, except we don't know Y, right? So we're going to say Y is equal to 1/2, what? 110 minus 30. Because it's an external intersection of these two chords or rays or whatever. They're external. So because of that, we're going to have 2Y is equal to 110 minus 30 is 80. And Y then, therefore, is equal to 40. Okay, pretty straightforward. Okay, example 2, it's a real world problem. It says, you focus your camera on a fountain. Your camera is at the vertex of the angle formed by tangents to the fountain. You estimate that the angle is 40 degrees. Okay, so here we see it right down here. You're standing over here somewhere with your camera, and you're thinking that the angle between these two tangent lines from the camera to A and the camera to B, those tangent lines is about 40 degrees. So what is the measure of the arc of the circular basin of the fountain that will be in the photograph? So if you're standing in the front, we're going to assume that you're going to be seeing this part down here. And maybe I should draw it in red, I guess, maybe a different color. It's going to be this front part here, because the back part, you're not going to be able to see it. That's assuming the fountains have got a high wall, right? You can't see the back half. So how are we going to determine, it says so, what is the measure of the arc of the circular basin of the fountain that it will be in the photograph? They want to know how big is this arc. Well, it says let the measure of AB equal to X. Okay, we want X to be AB. It says it right here. Let X equal the measure AB. Well, there are two ABs, are there not? There's the AB here in front, and then there's the AB around the back. So we're distinguishing between the two of them by putting the E in here. So we can go AEB versus just plain AB. Okay. So then, the measure of AEB is equal to 360 degrees. It's the entire fountain, 360 degrees going around the fountain, minus the piece that we want, the X piece. So this back piece from here to here is equal to the whole circle, all the way around, the circle all the way around, minus the front half. So whatever that is, we don't know. All we know is it's 360 minus X. Okay? So now we're going to look at the numbers. 40 is the angle here. We know that this angle right here that we're looking for, we're going to be able to determine it from this fountain. What this 40 is equal to is not E, but AEB minus X, or just the AB. That's what this, and it's half of that. So 1/2 of AEB minus X is what is 40 degrees. So let's see what it says in the problem. It says 40 degrees is 1/2 the measure of AEB minus AB. That's what I just said. The 40 degrees is equal to 1/2 this piece around the top versus AB on the bottom. So now we'll do some substitution from theorem 11.11-2. 40 is equal to 1/2 of 360 minus x. So this part up here, I'm going to change colors again. Let's change to yellow. The part up here, all the way around up here, is equal to what? It's equal to 360. This is x minus the x. That's what this piece sees. But in order to get the 40 degrees, we have to take the outer piece and subtract the inner piece. The outer piece minus the inner piece. Well, the first mathematics we did was to determine what the outer piece was, and the outer piece is 360 minus the inner piece. Now we have AEB, and then we subtracted x. But the equation for this angle down here, the 40 degrees, is 1/2. Right? So you have to take the x away. It's not one, I'm sorry, not 1/2. It's this value out here minus this value. So that ends up being right here, 1/2, 360 minus x minus another x. Because to get the outer piece, you needed 360 minus x. And now and that piece is the real outside piece. Now you have to subtract the inside piece. So that gives us 1/2. After we do that, that gives us 1/2, 360 minus 2x, because we're subtracting x twice. So given that, if we resolve the half, simplify and get rid of the half, we're going to, and using distributive property, we're going to divide the half out. We're going to get 40 is equal to 180 minus x, because we divided both by 2. 360 and the 2. Now the half is gone, and now we can take the 180 and move them around to whatever to simplify this. X ends up being 40 degrees, a 40 degree arc. So A is a 40 degree arc, will be in the photograph. Okay, example 2, check your understanding. So they'd like you to try this on your own. This time, though, for the photograph, they want a 160 degree arc of the basin. So the question, first there's two-part question. Should you move forward or backwards? You need to get the 160. Right now you're getting 140 with the last slide. What do you have to do to get 160? Move farther away or move closer? That's one question. And then the other thing is, what angle should the tangents form? So to get the 160 degrees around the fountain. So what you're talking about is a larger arc closer to the camera. So go ahead and try it. When you come back, we'll try it together or look at it. Okay, I'm assuming you tried it. So let's talk about this. In order to get a larger arc in the front, close to the camera, if you move closer, what would happen? Well, I'm going to draw on this. Your tangent lines, if you say you brought your focal point in here, your tangent lines would get like this, right? They would move from out here to like here, wouldn't they? And the same thing would be here. It would go up here, and it would touch here as opposed to here. So that means that this angle is getting smaller as you move closer. As you move farther away, they would tend to go up the side of the circle or the fountain. So moving away, A-W-A-Y, that's the part A's answer. Move away to get a bigger area of that fountain, of the front arc. Okay. Now we want, what is the measure to get that 160 degrees? Well, the measure we want is x, and it is equal to 1/2 what? It's always equal to 1/2, right? Equal to, we need, just as the previous slide, we need the outer piece, whatever the outer piece is. I'm going to go to red. Whatever, I think. Anyway, we're going to go from whatever the outer piece is. It's going to go now out here all the way around. To get it, you got to go down to here. I'm making that up, but whatever it is, I'm not sure. Maybe it's over here. It actually should be higher, probably. I'll draw it higher. That's what it should be. So it's up here. So to get the upper piece, you have to take 360 degrees and subtract the bottom piece. Well, what is the bottom piece? It's 160 degrees. So AEB excuse me please, 360 degrees minus 160, 360 minus 160, well, I'm too close, minus what? Well, it's the outer piece, the AEB piece, which we just came up with here is 360 minus 160. That's the outer EB part. And now we have to subtract the X, the AB part, minus another 160. So that's why the two lines over here, okay? So now that's 360 minus 160 minus 160. Minus 160 minus 160 is what? 200, right? 220. So X is equal to 1/2 360 minus 320. X equals 1/2 40. So X equals 1/2 of 40 is 20. Do you see that? Okay. Okay, objective 2A, finding segment lengths. From a given point P, you see P right now is over here, it's inside of our circle. Point P is right here inside the circle. You can draw two segments to a circle along infinitely many lines. So from P, you can see there's A3 and B3, a PA3, PB3, PA1, PB1, right? So there's a line going through the point intersecting the circle. Okay, so, and that point creates many different lengths of PAs to PBs, so to speak. So, for example, PA1, which is this one right here, PA1, and PB1 lie along one such line. So one of these chords that went through a chord through the circle that intersected P, that P was part of that chord, right? Lie along one such line. So theorem 1112 states that it's a surprising result that no matter which line you use, whether it's the PA2, PB2, PA3, PB3, whichever one you use, you could draw as many as you wanted and name them as many times as you wanted to. The product PA times PB is constant. So PA times PA1 times PB1, that product, let's say it turns out to be 20, would be the same as PB3 times PA3, which would also be multiplied together and give you 20. It's the same constant. Very interesting. So now theorem 1112 says for a given point and circle, the product of the lengths of the two segments from the point to the circle, that's what we've been talking about, is constant along any line through that point and the circle. It's amazing. So number one here, it says A times B is equal to C times D. So here's A times B, whatever those lengths are, let's say 20 and 10. That's 200. Would mean that C times D would also have to be equal to 200. Whatever the lengths are, I don't know, but they'd have to equal 200. Now there's a difference. That's when the point's inside the circle. When the point's outside the circle, you handle it a little differently. Outside the circle, it's looking here for it's X plus W times the quantity, X plus W times W. For this line here, P's, whatever this is, Z, Y here is, it's Z plus Y times Y. X plus W times W. Okay? It's that simple. So, also, a third option is when you have the tangent. So one of your lines creates a chord segment in the circle, a chord. The tangent never enters the circle. It just goes up and touches the circle, almost like Y is touching the circle in a strange way, but that kind of a thing. It never goes into the circle. So if that's the case, you get Y plus Z on this side, Y plus Z, and here's Y and Z, and you multiply the quantity of that times Y, and they'll be equal to the distance for the tangent from P to the circle squared, T squared. So when the point is inside the circle, the line segments when multiplied together are all equal if they go through that same point and intersect with the circle. When the point's outside the circle, basically you're talking about adding the distance inside the circle plus the distance outside the circle and multiplying those two added values by the part that's outside the circle. And when there's a tangent, just remember that the piece that goes inside the circle is handled the same as part 2, and if there's a tangent, it's just the tangent squared. Very, very interesting. Okay, objective 2b, finding segment lengths. The proof of theorem 11-12, 1, or I, or whatever that is, Roman numeral 1. Given a circle with chords A, B, and CD. You see those, A, B, and CD, the red and the blue chords, intersecting at P. Prove that A times B is equal to C times D. That's what we were saying in the previous slide. Okay, so draw the segment AC, or the segments AC and BD. So what they want you to draw is right here. Where's my pencil? There it is. They want you to draw this segment here and this segment here. Okay, and by doing that, and so it says draw those. It says angle A is now congruent to angle D. Angle A, that's this angle here, is congruent to angle D. Well, how is that congruent? And it says angle C. Does it say that too? It says angle C is congruent to B. Angle C is congruent to B. So let's go to the first one. Angle A congruent to angle D. Angle A is congruent to angle D because both of them have intercepted arcs as the same arc. So D, this one here is the angle D's intercepted arc is here. I just drew in blue. So the blue line here is for angle D, and the red line there is for angle A. So since they have the intercepted arc is identical, these angles are congruent. And B is from here, A to D is B, angle B. And for C is from A to D, the same thing. So this angle is congruent to this angle. This angle is congruent to this angle. So now we have all these congruent angles, okay? So that's what they've set off in this first line because they are inscribed angles and each pair intercept the same arc. Thus, triangle APC, we have two congruent angles. APC is similar, that triangle is similar to DPB because of, why? Because of the angle-angle similarity postulate. So we have two triangles with identical angles, What we don't know is how long the segments are. All we know is that the angles are identical, so they're similar. This angle will be the same in both. This angle here will be the same in both. We just don't know how long the sides are going to be. Okay? So the lengths of the corresponding sides of similar triangles are proportional, though. So what they're saying is that the length here, I'm going to change colors. Let's go back to green, maybe see how that goes. They're saying that this line here, this segment, AP, is proportional to AD because of these proportional triangles as what? As CD, as CP is proportional to BP. And there you have it right. The lengths of corresponding sides of similar triangles are proportional. So A divided by D, that's the proportionality, is the same as C divided by B. And given that A divided by B is equal to C divided by B, therefore cross multiplying, A times B is equal to C times D. And that's where you get the A times B is equal to the C times D. It's amazing. I love this. Okay, example 3, finding segment lengths. They say this is an algebra problem. Finding the value of the variable. If the answer is not the whole number, round to the nearest tenth. Okay? So based on what we did before when we were looking at we were just studying a previous slide, we now found that when the intersection is outside the circle, we add these two. So it's the inside the circle piece plus the outside the circle piece times the outside the circle piece, right? And again, it's the inside plus the outside times the outside. So what does that look like? 8 plus 6 times the outside times the 6 is equal to 7 plus y, right here, times the 7. So now we're going to solve for y. So we're going to get 84 is equal to 7 times 7 is 49 plus 7y. We're going to move the 49 to the other side, and we're going to get 35 is equal to 7y. And we're going to divide both sides by 7, and we're going to get y equal 5. Just a little bit of manipulation on the numbers here. Let's look at this other one. This is this case 3 in our theorem. So let's look at this. This is 8 plus 16. 8 plus 16 times the 8. That's right here. That's equal to z squared, they said before. We talked about z squared. So 192 is z squared. 13.9 is approximately equal to z. So z is approximately 13.9. Okay, check your understanding. Example 3. Find the values of the variables to the nearest tenth. So go ahead, stop the video and try these. Remember, one of these, the dot is outside, and the other one, the dot is inside. So you handle them differently. Go ahead and give them a try. Okay, I'm going to assume you've done that and you've come back. So let's work them together. So hopefully there's enough room for this. Let's try. So it's, what are the two equations? What are we going to equal? What equal to what? So it's going to say 20 plus 14 times 14 is equal to the quantity x plus 16 times 16. So there it is. Solve it. 14 times the quantity 20 plus, or 34 times 14 is 476. And 16 times x is 16x. Plus 16 times 16 is 256. So we have to get the x by itself. So we're going to do that by subtracting 256. So 476 minus 256 is equal to 16x. So now this is equal to 220 is equal to 16x, and x, divide both sides by 16, you get x equals 13.7. Let's do B. This is handled differently because now it's part A minus or times part B, right? Part A times part B. So part A, I'm going to say m times 6.5 is equal to 3 times 7. 3 times 7. So I'm going to rewrite this. 6.5 m is equal to 21. So what is m equal to? M is equal to divide both sides by 6.5. And m is equal to 3.2. Okay? Okay, example 4, it's a real world problem. It's a bridge design, right? The arch of the Taikobashi Bridge is an arc of a circle. A 14-foot chord is 4.8 feet from the edge of the circle. Find the radius of the circle. So we see it here with this 14-foot chord, and the arch up to from the chord is 4.8 feet. It says draw the diagram that shows a 14-foot chord. 7 plus 7 is 14 feet. And 4.8 feet below the top of the circle. Let x represent the length of the part of the diameter from the chord to the bottom of the circle. Use x and theorem 1112 to find the radius. Okay, so we're looking for the radius, to find the radius. It says here. I thought they were going to want the diameter, but let me just give me 1 second. I'm looking to make sure I'm in the right spot. Yep, they want the radius. Okay, the radius is I see it down here. Radius is about 7.5 feet. We wrote here, right? So how did they work this out? They said 4.8 times x. So using theorem 1112.1, 4.8 right here, 4.8, and x, right? That x times 4.8 is 4.8x right here is equal to 7 times 7, 49. 4.8x is equal to 49. X then is equal to 49 divided by 4.8, which is 10.2. The diameter is equal to 10.2 plus 4.8. It's 15 feet. We just added the segments together. And now the radius is half the diameter. So it's about 7.5 feet. Is that clear to everyone? I think it should be. We multiplied the 4.8 times the x and the 7 times the 7 and set them equal to each other. And when you do that, you end up with solving for x, and x ends up being some value 10.2 feet, and 10.2 feet plus 4.8 feet is the total diameter. And then we can find the radius by just taking half the diameter. Okay, example 4a I have here. Check your understanding, right? So what we want you to do is stop the video, take some time and read this over and see if you can come up with a solution for x. The directions say, the basis of a design for a rotor for a Wankel engine is the equilateral triangle. It's an equilateral triangle. Each side of the triangle is a chord of an arc of a circle. The opposite vertex of the triangle is the center of the arc. So you see that they're back down here, the center down here. Okay, if you swung this arc, this guy here, he follows the arc. Okay, so this arc is created by this 8-inch length chord. Okay. The opposite vertex of the triangle is the center of the arc. The diagram at the right and has each side of the equilateral triangle is 8 inches long. So it says, use what you know about equilateral triangles to find the value of x. Okay, go ahead and stop the video. When you come back, we'll continue. Okay, I assume you've done your work now, so let's take a look at this. So we read the directions, right? The key here is the opposite vertex. That's at the bottom. Is the center. Is the bottom down here at the very bottom. All right, down here. Okay, we're talking about that. And that in the diagram at the right, each side of the equilateral triangle is 8 inches long. So it's 8, 8, and 8. Okay. Use what you know about equilateral triangles to find the value of x. So what do we know? Equilateral triangles have 3 equal sides, but we were given that, and 3 60-degree angles. Okay. The altitude of an equilateral triangle, so we're going to say the altitude coming right down here. I'm going to draw it in, but it's not going to be very good, but you know what I'm doing. The altitude coming right down here. Oops. Should I start over? Maybe I should do that over again. I should do that over. Let's see if I can do that over again. Get the line over here. I have no ruler or anything in this program here to draw this. So if I do it in little bunches, maybe I can do it. You get the picture. This is the altitude. You can do that on any one of these sides, but this is the one I'm choosing. So it says the altitude, where were we here? They have 3 equal sides, 3 60-degree angles. The altitude of an equilateral triangle divides it into 2 30, 60, 90 triangles. So here we are. So these are 60-degree angles, so that means that this one here is 30, and this is 30. This is your 60. Okay, these are your 60s. And here, and this is your 90 right here. Okay. The opposite side of the 30-degree angle, so down here, pick either one you want. This is maybe a nicer one over here. This one right here, this 30-degree angle, the opposite side, we're talking about this section right through here, is half the length of the hypotenuse. Well, the hypotenuse is along this radii here, and it's half that length. And we kind of know that because we see that this is split right down the middle. So if these are 8 inches, 8 inches for this chord right here is 8 inches, then from X to the end of the chord here is 4 inches. And we see here that these are congruent too, right? They've marked them as congruent for us. So this is 4 inches. So knowing that that's 4 inches, and it says, and the side adjacent to the 30-degree angle. So now they're talking about what's the side adjacent? They're talking about the altitude. The altitude is the side adjacent to the 30-degree angle. Is the square root of 3 times the opposite side's length. Well, the opposite side, this is the opposite over here. I'm going to put red on it now. So opposite, adjacent, right? So the length of the adjacent, or the altitude in this case, is the opposite times the square root of 3. Right here, square root of 3. I'll read that again now. The side opposite the 30-degree angle is half the length of the hypotenuse, which is 4 inches, and the side adjacent to the 30-degree angle is square root of 3 times the opposite side's length. Okay, so it's 4 square roots of 3. Since X and the altitude lie on and form a radius, which is 8 inches long, X is equal to 8 the length of the radius, minus 4 square roots of 3, or approximately 1.1 inches. So we decided here that this length here is 4 square roots of 3. And x, you add this and a little bit of x up here. And then you get, that's 8 inches. We know that this radius from the center to the arc is 8 inches. So if you take 8 inches and subtract the full minus the square root of 3, you're going to end up with what's left is x. And that is 1.1 inches. Okay, part B of that same problem says critical thinking here. It says copy the diagram to complete the circle given with a given center. So the center is pointed to right here. What they're asking you to do is to draw a big circle. Instead of just having the little arc, just go around completely and make a 16-inch circle. Okay, that's because of what they want you to do here. So you've made this circle, the circle with a center. Okay, then use theorem 11-12 to find the value of x. Show that your answers to parts A and B are equal. So what you're going to do is you're going to come up with the same answer, which was 8 minus 4 square roots of 3, or approximately 1.1 inches. That's what we came up with last time. So now you're going to, what they want us to use is theorem 11-12, which is kind of going to take into account here this point right here, right there, because now we're going to have a long diameter going through the center all the way across to the other side of the circle. So if I draw it, I'm going to draw a little one over here. You're going to have say this is a 16-inch circle. You got that little bit of 8, that little bit of x, and then you're going to have the 8 inches to here, plus another 8 inches down here. So you're going to have a chord across here. And it's going to look something like this. X is up here, and 4 square roots of 3 plus 8 inches is this bottom piece. Okay? So, so let me say, so now we've got that. Show that your answers are the same. So here's what we're going to do here. We're going to assume that we've drawn a 16-inch circle about the point marked center, okay, and extended the line labeled X, which is the piece we're looking for, extended that line labeled X along the diameter through to the other side of the circle, which is what I just kind of drew. Excuse my artwork, but down here in this little picture. Through the other side of the circle, thus making a 16-inch circle that is made up of segments x and 16 minus x along the diameter. Okay, so we've got this long line that we drew in there. Additionally, the chord related to the arc intersects the point at the junction of x and 16 minus x. So what they're saying here is that this chord right here, where's my pencil? There it is. That the chord right here intersects the diameter that we drew, that goes down here, all the way down, all the way down 16 inches. Okay? I'm going to erase that little smudge mark there. But you get, It's weird how this pen does that. I got to figure out why that does that. I don't know. Probably need a new tablet. Anyways, so that's what they're basically want you to know, that point right there, that intersection of that diameter and that chord, that's the important point. You can call it point P if you want, but I'm not calling it any given point. Okay, so additionally, the chord related to the arc intersects the point at the junction of x and 16 minus x. That's that diameter down there we were talking about. Okay, given that and theorem 11-12, let's solve for x. So now we're going to solve for x. So the theorem 1112 said that any point inside the circle with lines extending out to the circle in opposite directions, that the product of those two segments are equal. You remember that. So we're going to say here that 16 x, which is the little piece, and then the point P, or point at the 8-inch mark there, point, I'll call it P. The point P, it's 16 minus x is the other side extending out from P down to the other side of the circle. So that's the one segment, two segments we have, the A and B segments, the x and the 16 minus x piece. And then the chord is another line going through that point within the circle, and that's 4 and 4. That 8-inch is divided in the middle, so it's 4 and 4. Divided at the point P that we're talking about. I'll draw P on there so everybody knows I'm talking about point P. I'm going to use red ink, and I'm going to say point P is right there, okay? Point P. Okay, given that, we're going to do some mathematics. X times 16 minus x, that's part of this theorem 1112, is equal to 4 times 4. Okay, the two pieces, which are 4 inches long, and the x and the 16 minus x piece going in the other direction. So when we multiply that to solve it, we get using the distributive property here, we have 16x minus x squared is equal to 4 times 4, which is 16. And now we're still solving for x. So now we're going to bring the 16 to the opposite side, and we're going to have minus x squared plus 16x minus 16 equals 0. Well, in my case, I've chosen to get rid of the negative x squared, and it's now, I've divided everything by a negative 1, or multiplied everything by a negative 1, however you like to say it. So now I have x squared minus 16x plus 16 equals 0. The reason I especially want to do that is we're going to use the Pythagorean theorem, and Pythagorean theorem likes b's, which are negative, but it's little, you have to deal more with signs more if your x squared and your constant are negative. So given that, we have x squared minus 16x plus 16 is equal to 0, and we're going to use Pythagorean theorem to solve for x. So on the other side here, we've taken and we've got it. The Pythagorean theorem says b minus b, and b is minus 16. So it's minus a minus 16. Okay, plus or minus the square root of b minus 16 squared minus 4 times a is a 1, times c is a 16. And that's all divided by 2 times a, and a is a 1. Okay, so now if you simplify that, we're going to get minus 16, which is plus 16, plus or minus b minus b squared, which is 256, minus 4 times 1 times 16, minus 64, all divided by 2. So now when we simplify it even a little further, we're going inside the radical now. We're going to have 16 plus or minus the square root of 192, okay, divided by 2. That's what we have here. So we step to the next step. X equals 16 plus or minus the square root of 64 times 3. 192 is 64 times 3. Okay, 64 is a perfect square. And this is all divided by 2. So we can take the 64 out, and we can call this 16 plus or minus 8. Take the square root of 64 and get 8 times the square root of 3. What's left? Divided by 2. Now when we do that, we have 8 plus or minus 4 square roots of 3 and that's our solution. The answer here is x is equal to 8 minus 4 square roots of 3. And 8 plus 4 square roots of 3 is not reasonable because the combined length, 8 plus the almost 8 again, is longer than the radius. So you can't have it longer than the radius. So it has to be minus 4 square roots of 3. Okay, so that is our answer there. And that, if you look at that answer, it's going to be the same. 8 minus 4 square roots of 3 is 1.1. So they're the same. They're equal. Okay?